Good morning everyone. Today we are going to read our Unit 9 Hydrogen. Hydrogen is the most abundant element in the universe and the third most abundant on the surface of the globe, is being visualized as the major future source of energy. Hydrogen has the simplest atomic structure among all the elements around us in nature. In atomic form, it consists of only one proton and one electron. However, in elemental form, it exists as a diatomic molecule and is called dihydrogen. It forms more compound than any other element. Do you know that the global concern related to energy can be overcome to a great extent by the use of hydrogen as a source of energy? In fact, hydrogen is of greatest industrial importance, as you will learn in this unit. Position of hydrogen in the periodic table. Hydrogen is the first element in the periodic table. However, its placement in the periodic table has been a subject of discussion in the past. As you know by now that the elements in the periodic table are arranged according to their electronic configuration. Hydrogen has the electronic configuration 1s1. On one hand, its electronic configuration is similar to the outer electronic configuration ns1 of alkali metals, which belongs to the first group of the periodic table. On the other hand, like halogens with ns2 np5 configuration belonging to the 17th group of the periodic table, it is short by one electron to the corresponding noble gas configuration helium 1s2. Hydrogen therefore has resemblance to alkali metals, which lose one electron to form unipositive ions, as well as with halogens, which gain one electron to form uninegative ion. Like alkali metal, hydrogen forms oxides, halides and sulfides. However, unlike alkali metal, it has a very high ionization enthalpy and does not possesses metallic character under normal conditions. In fact, in terms of ionization enthalpy, hydrogen resembles more with halogens. Like halogens, it forms a diatomic molecule, combines with element to form hydrides and a large number of covalent compounds. However, in terms of reactivity, it is very low as compared to halogens. In spite of the fact that hydrogen to a certain extent resembles both with alkali metals and halogen, it differs from them as well. Now the pertinent question arises as where should it be placed in the periodic table? Loss of electron from hydrogen atom result in the nucleus H positive of almost same to 1.5 into 10 raised to power minus 3 picometer size. This is extremely small as compared to normal atomic and ionic size of 50 to 200 picometer. As a consequence, hydrogen or H positive does not exist freely and is always associated with other atoms or molecules. Thus, it is unique in behavior and is placed best placed separately in the periodic table. Isotopes of hydrogen. Hydrogen has three isotopes: protium, hydrogen 11, deuterium, hydrogen 12 or D, and tritium, hydrogen 13 or T. Can you guess how these isotopes differ from each other? These isotopes differ from one another in respect of the presence of neutrons. Ordinarily, hydrogen protium has no neutrons. Deuterium, also known as heavy hydrogen, has one or and tritium has two neutrons in the nucleus. In the year 1934, an American scientist, Harold C. Urey, got Nobel Prize for separating hydrogen isotope of mass number 2 by physical method. The predominant form is protium. Terrestrial hydrogen consists 0.0156% of deuterium, mostly in the form of Hd. The tritium concentration is about 1 atom per 10 raised to power 18 atoms of protium. Of these isotopes, only tritium is radioactive and emits low energy beta particles T half 12.33 years. Occurrence. Dihydrogen. Dihydrogen is the most abundant element in the universe, 70% of the total mass of universe, and the principle of element is Since the isotopes have the same electronic configuration, they have almost the same chemical properties. The only difference is in their rates of reaction, mainly due to their different enthalpy of bond dissociation. Table 9.1. However, in physical properties, these isotopes differ considerably due to their large masses difference. Preparation of dihydrogen H2. There are a number of methods for preparing dihydrogen from metals and metal hydrides. 9.31 Laboratory preparation of dihydrogen. It is usually prepared by the reaction of granulated zinc with dilute hydrochloric acid. Zinc plus 2H positive gives zinc 2 positive plus hydrogen gas. Second, it can also be prepared by reaction of zinc with aqueous alkali. Zinc react with 2NaOH gives sodium zincate plus hydrogen. Commercial production of dihydrogen. The commonly used process are outlined below. First, electrolysis of acidified water using platinum electrodes gives hydrogen. 2H2O on electrolysis gives 2H2 plus O2. High purity 99 more than 99.95% dihydrogen is obtained by electrolyzing warm aqueous barium hydroxide solution between nickel electrodes. It is obtained as a byproduct in the manufacturing of sodium hydroxide and chlorine by the electrolysis of brine solution. During electrolysis, the reaction that take place are at anode 2Cl minus gives Cl2 plus 2 electron. At cathode, 2 water molecule plus 2 electron gives H2 plus 2 OH negative. The overall reaction is given. Reaction of steam on hydrocarbons or coke at high temperature in the presence of catalyst yield hydrogen. The mixture of CO and H2 is called water gas, as this mixture of CO and H2 is used for the synthesis of methanol and a large number of hydrocarbons. It is also called synthesis gas or syngas. Nowadays, syngas is produced from sewage, sawdust, scrap wood, newspaper. The process of producing syngas from coal is called coal gasification. Carbon plus H2O at 1270 Kelvin temperature gives carbon monoxide gas plus hydrogen gas. The production of dihydrogen can be increased by reacting carbon monoxides of syngas mixture with steam in presence of the iron chromate as catalyst. As we can see, the reaction CO plus H2O gives CO2 plus hydrogen at 673 Kelvin temperature. This is called water gas shift reaction. Carbon dioxide is removed by scrubbing with sodium arsenide solution. Presently, 77% of the industrial dihydrogen is produced from petrochemical, 18% from coal, 4% from electrolysis of aqueous solution and 1% from other sources. Properties of dihydrogen. Physical properties. Dihydrogen is a colorless, odorless, tasteless, combustible gas. It is lighter than air and insoluble in water. Its other physical properties along with those of deuterium are given in table 9.1. As we can see the table 9.1. Now we have to move to the chemical properties of dihydrogen. The chemical behavior of dihydrogen, and for that matter any molecule, is determined to a large extent by bond dissociation enthalpy. The HH bond dissociation enthalpy is the highest for a single bond between two atoms of the element. What inferences would you draw from this fact? It is because of this factor that the dissociation of dihydrogen into its atom is only 0.081% around 2000 Kelvin, which increases to 95.5% at 5000 Kelvin. Also, it is relatively inert at room temperature due to high HH bond enthalpy. Thus, the atomic hydrogen is produced at a high temperature in an electric arc or under ultraviolet radiations. Since its orbital is incomplete with 1s1 electronic configuration, it does combine with almost all the elements. It complies reactions by loss of only one electron to give H positive, gain of an electron to form H negative, and sharing of electron to form single covalent bond. The chemistry of dihydrogen can be illustrated by the following reaction. Number 1. Reaction with halogen. It reacts with halogen X2 to give hydrogen halides HX. Example, when H2 gas is react with X2, it gives 2HX gas. X can be fluorine, chlorine, bromine, iodine. While the reaction with fluorine occurs even in dark with iodine, it requires a catalyst. Reaction with dioxygen. It reacts with dioxygen to form water. The reaction is highly exothermic. 2 hydrogen gas plus O2 in presence of catalyst or heating gives 2 molecules of water. Reaction with dinitrogen. With dinitrogen, it forms ammonia 3H2 plus N2 at 673 Kelvin temperature, 200 atmospheric pressure gives 2NH3 ammonia. This method is for the manufacturing of ammonia by the Haber process. Reaction with metals. With many metals, it combines at a high temperature to yield the corresponding hydrides. H2 plus 2M gives 2MH solid, where M is an alkali metal. Reaction with metals, ions and metal oxide. It reduces some metal ions in aqueous solution and oxides of metal less active than iron into corresponding metals. Hydrogen with palladium 2 plus gives palladium solid plus 2H positive aqueous. Reaction with organic compound. It reacts with many organic compound in the presence of catalyst to give useful hydrogenated products for commercial importance. For example, in metallurgical process, it is used to reduce heavy metal oxide to metals. Atomic hydrogen and oxyhydrogen torches find use for cutting and welding purposes. Atomic hydrogen atom produced by dissociation of dihydrogen with the help of an electric arc are allowed to recombine on the surface of the welded to generate the temperature of 4000 Kelvin. It is used as a rocket fuel in the space research. Dihydrogen is used in fuel cells for generating electrical cell energy. It has many advantages over the conventional fossil fuels and electric power. It does not produce any pollution and release great energy per unit mass of fuel in comparison to gasoline and other fuels. Now we have to move to our next topic, hydrides. Dihydrogen under certain reaction condition combined with almost all elements except noble gases to form binary compound called hydrides. If E is the symbol of element, then hydride can be expressed as EHX. Example, magnesium hydride MgH2 or E capital E small m H small n. Example, B2H6. The hydrides are classified into three categories: ionic or saline or salt-like hydrides, covalent or molecule hydrides, metallic or non-stoichiometric hydrides. Number 1. Ionic or saline hydrides. They are stoichiometric compounds of dihydrogen formed with most of the S block elements, which are highly electropositive in character. However, significant covalent character is found in the lighter metal hydrides such as lithium hydride, barium hydride and magnesium hydride. In fact, barium hydride and magnesium hydride are polymeric in structure. The ionic hydrides are crystalline, non-volatile and non-conducting in solid state. However, their melts conduct electricity and on electrolysis liberate dihydrogen gas at the anode, which confirm the existence of the H negative ion. As we can see the reaction, when 2H negative melt at anode, it gives hydrogen gas plus 2E negative. Saline hydrides react violently with water producing dihydrogen gas. NaH plus H2O gives NaOH plus hydrogen gas. Lithium hydride is rather unreactive at moderate temperature with O2 or chlorine. It is therefore used in the synthesis of other useful hydrides. Example, 8LiH plus Al2Cl6 gives 2 lithium aluminium hydride plus 6 LiCl. 2LiH plus B2H6 gives 2LiBH4. Second, covalent or molecule hydrides. Dihydrogen form molecule compounds with most of the p block elements. Most familiar examples are CH4, NH3, H2O, and HF. For convenience, hydrogen compounds of non-metal have been considered as hydrides. Being covalent, these are volatile compounds. Molecular hydrides are further classified according to the relative number of electrons are bonded to their Lewis structure into electron deficient, electron precise, and electron rich hybrid. An electron deficient hydride as the name suggests has few electrons for writing its conventional Lewis structure. Diborane B2H6 is an example. In fact, all elements of group 13 will form electron deficient compound. What do you expect from their behavior? They act as Lewis acid, example electron acceptors. Electron precise compounds have the required number of electrons to write their conventional Lewis structure. All elements of group 14 form such compounds, example CH4, which are tetrahedral in geometry. Electron rich hydrides have excess electrons which are present as lone pairs. Elements of group 15-17 form such compounds. NH3 has one lone pair, H2O2, HF3 lone pair. What do you expect from their behavior of such compounds? They will behave as Lewis based at electron donors. The presence of lone pair on highly electronegative atoms like nitrogen, oxygen, fluorine hydrides results in the hydrogen bond formation between the molecule. This leads to the association of molecules. Metallic or non-stoichiometric or interstitial hydrides. These are formed by many D and F block elements. However, the metals of group 7, 8 and 9 does not form hydrides. Even from group 6 only chromium forms CRH. These hydrides conduct heat and electricity, though not as efficiently as their parent metals do. Unlike saline hydrides, these are almost always non-stoichiometric, being deficient in hydrogen. For example, LAH, YBH, TIH, JRH, VH, NIH, PDH. In such hydrides, the law of constant composition does not hold good. Earlier, it was thought that in these hydrides, hydrogen occupies interstices in the metal lattice, produce distortion without any change in its type. Consequently, they were termed as interstitial hydrides. However, recent studies have shown that except for hydrides of nickel, palladium, Ce and Ac, other hydrides of the class have lactic different from that of the parent atom or metal. The property of absorption of hydrogen or transition metals is widely used in catalytic reduction and hydrogenation reactions for the preparation of large number of compounds. Some of the metals, palladium, platinum, can accommodate a very large volume of hydrogen and therefore can be used as its storage media. This property has high potential for hydrogen storage and has a source of energy. Water. A major part of all living organism is made up of water. Human body has about 65% and some plants have a much as 95% water. It is a crucial compound for survival of all life forms. It is a solvent of great importance. The distribution of water over the earth crust is not uniform. The estimated world water supply is given in table 9.2. As we can see the table. Physical properties of water. It is a colorless and tasteless liquid. Its physical properties are given in table 9.3 along with physical properties of heavy water. The unusual properties of water in the condensed phase, liquid and solid states are due to the presence of extensive hydrogen bonding between water molecules. This leads to high freezing point, high boiling point, high heat of vaporization and high heat of fusion in comparison to H2S and H2SC. In comparison to other liquid, water has a higher specific heat, thermal conductivity, surface tension, dipole moment and dielectronic constant, etc. These properties allow water to play a key role in the biosphere. Table 9.3. The heat of vaporization and heat capacity are responsible for the moderation of climate and body temperature of living beings. It is an excellent solvent for transportation of ions and molecules required for plant and animal metabolism. Due to hydrogen bonding with polar molecules, even covalent compounds like alcohol and carbohydrates dissolve in water. Structure of water. In the gas phase, water is a bent molecule with bond angle of 104.5 degree and OH bond length of 95.7 pm as shown in figure 9.1 is highly polar molecule. Its orbital overlap picture is shown in figure 9.1c. In the liquid phase, water molecules are associated together by hydrogen bonds. The crystalline form of water is ice. At atmospheric pressure, ice crystallizes in the hexagonal form, but at very low temperature it condenses to form cubic form. Density of ice is less than that of water, therefore an ice cube floats on water. In winter season, ice formed on the surface of a lake provides thermal insulation which ensures the survival of aquatic life. This fact is of great ecological significance. Structure of ice. Ice is highly ordered three-dimensional hydrogen bonded structure as shown in figure 9.2. This is the structure of ice. Chemical properties of water. Water reacts with a large number of substances. Some of important reactions are given below. First, amphoteric nature. It has the ability to act as an acid as well as base, that it behaves as an amphoteric substance. In the Bronsted sense, it acts as an acid with NH3 and a base with H2S. We can see the reaction. H2O with NH3 gives OH negative plus NH4 positive. H2O with H2S gives hydronium ion H3O positive plus SS negative. The autoprotolysis self-ionization of water takes place as follows. Redox reactions involving water. Water can be easily reduced to dihydrogen as highly electropositive metals. Example, H2O with 2 sodium gives 2 NaOH plus hydrogen gas. Thus, it is a great source of dihydrogen. Water is oxide to O2 during photosynthesis. 6CO2 plus 12H2O gives C6H12O6 plus 6H2O plus 6O2. With fluorine also it is oxidized to O2. Third, hydrolysis reaction. Due to high dielectronic constant, it has a very strong hydrating tendency. It dissolves many ionic compounds. However, certain compounds and some ionic compounds are hydrolyzed in water. P4O10 with 6H2O gives 4H3PO4. Hard and soft water. Rainwater is almost pure, may contain some dissolved gases from the atmosphere. Being a good solvent when it flows on the surface of earth, it dissolves many salts. Presence of calcium and magnesium salt in form of hydrogen carbonate, chloride and sulfide make water hard. Hard water does not give lather with soap. Water free from soluble salts of calcium and magnesium is called soft water. It gives lather with soap easily. Hard water forms scum precipitate with soap. Soap containing sodium stearate C17H35COONA reacts with hard water to precipitate out calcium and magnesium stearate. It is therefore unsuitable for laundry. It is harmful for boilers as well as because of decomposition of salts in the form of scale. This reduces the efficiencies of the boiler. The hardness of water is of two types: temporary hardness and permanent hardness. Temporary hardness. Temporary hardness is due to presence of magnesium and calcium hydrogen carbonate. It can be removed by first boiling. During boiling, the soluble magnesium HCO3 whole twice is converted into soluble MgOH whole twice, and calcium HCO3 twice is changed into insoluble calcium carbonate. It is because of high solubility product of MgOH whole twice as compared to that of MgCO3 that MgOH whole twice is precipitated. These precipitates can be removed by filtration. Filtrate thus obtained will be soft water, as we can see. Second, Clark method. In this method, calculated amount of lime is added to hard water. It precipitates out calcium carbonate and magnesium hydroxide, which can be filtered off. Third, ion exchange method. This method, also called zeolite permute process. Hydrated sodium aluminium silicates is zeolite permutate. For the sake of simplicity, sodium aluminium silicate NaAlSiO4 can be written as NaZ. When this is added in hard water, exchange reactions take place. Permutate and zeolite is said to be exhausted when all the sodium in it is used up. It is regenerated for further use by treating with an aqueous solution of sodium chloride solution. Synthesis resin method. Nowadays, hard water is softened by using synthetic cation exchangers. This method is more efficient than zeolite process. Cation exchange resins contain large organic molecules with SO3H group and are water insoluble. Ion exchange resin RSO3H is changed to RNA by treating it with NaCl. The resin exchange Na positive ions with Ca2 positive and Mg2 positive ions present in the hard water to make the water soft. Here R is the resin anion. The resin can be regenerated by adding aqueous NaCl solution. Pure demineralized deionized water free from all soluble mineral salt is obtained by passing water successively through a cation exchange in the H positive form and an anion exchange in the OH negative form resins. In this cation exchange process, H plus changes for Na positive, Ca2 positive, Mg2 positive and other cations present in water. This process results in proton release and thus make the water acidic in the anion exchange process. As we can see the reaction, RNH3 positive dot OH negative plus X negative gives RNH3 positive dot X negative plus OH negative. OH exchanges for anions like Cl minus HCO3 negative, SO4 2 minus etc. present in water. OH ions thus liberated neutralize the H positive ions set free in the cation exchange. H positive plus OH minus gives water. The exhausted cation and anion exchange resin beds are regenerated by treatment with dilute acid and alkali solutions respectively. Hydrogen peroxide. Hydrogen peroxide is an important chemical used in pollution control treatment of domestic and industrial effluent.